who is there, I think, and she's going to talk about continuous Kendall-shape variational autoencoders. She's from Amsterdam University. Please.
Hi, thank you for the introduction. Hi, I'm Sharvari, and I'll be talking about continuous Kendall-shape VAE. Okay, and this work was done alongside my advisors, Jakub Tomczak and Eric Beckers, who is right here. Yeah, so the flow of the talk is the following. I will give a brief introduction followed by preliminaries. Then I'll talk briefly about the work that we did previously, which was Kendall-shape VAE, and then the extension, which is this work, continuous Kendall-shape VAE, and some experiments and the conclusion. Yeah, so the problem at hand, or the problem of interest here, was to do unsupervised learning and represent data in a low-dimensional space such that it has some kind of a geometric interpretation to it, and it has some meaningful representations. So the starting point here is VAEs. So what VAEs are good at doing is represent data in low-dimensional latent spaces, and they do so as the following. So VAE, as most of you all might know, consists of three things, like a generator, a prior, and an approximate posterior. And what it does is that given these images, for example, you're trying to have a low-dimensional space called a latent space, represent the data, learn a distribution over this rather than just an encoding that happens in an autoencoder. You learn the distribution, and then you compute the posterior, or approximate the posterior. And this is done by computing an evidence lower bound, which consists of an expectation maximization term, as well as a KL divergence over the prior and the posterior. So in some way, you want your distribution to be varied enough such that it can represent the data samples, but you don't want it to be too far from where you started with. So this is the term that exactly does that. And yeah, so, and what we do is, like, simply put, we just use neural networks to parameterize these two parts, which are encoder and decoder, which first lends to the latent space and such that then you can decode. Yeah. So, let's talk a bit about what kind of VAEs have come so far and if there are any cool geometrical ones. So the one of interest here, for example, is a hyperspherical VAE, as the name suggests, has a hyperspherical latent space. So instead of mapping to a normal Euclidean plane, you are mapping your latents to a sphere. Yeah, so we see that these hyperspherical latent spaces are good at representing data and can do so with fewer parameters than vanilla VAE. Then there's also this VAE, for example, is the Riemannian Hamiltonian VAE, which actually learns the Riemannian metric while training the VAE. But it has its own issues. For example, there are issues of scaling this VAE and does not work with all data types. Then came, for example, a spatial VAE, which can explicitly disentangle rotation and translation. So this was one of the first to do so. And the interesting thing for this is that once you can disentangle this, you can actually make it rotationally invariant, equivariant if you need them to be. And they do so, but the issue again with this VAE is that you need to train these separately. So the rotation part has to be trained separately, and then the translation part, which is not nice. Yeah, and then came EQ VAE, which starts with equivariant priors and tries to attempt at making a first VAE which is equivariant, but it turns out that it is not exactly equivariant to rotations, and does a good job at approximating so, and also manages to do so with different data types. Yeah, so these are some VAEs that try to incorporate some sense of either a different manifold or some kind of a compact structure, or try to go and do equivariance to rotation, translation, etc. Yeah, so I will focus a bit more on hyperspherical VAEs because our work kind of is inspired or takes this along. Yeah, so what is different about hyperspherical VAEs than the normal or vanilla VAEs is that instead of using a Gaussian distribution as a prior function, it uses a von Mises-Fisher distribution, as you can see here. And here the density function is then mapped on just directly, as you can see, on a hypersphere of dimension here, for example, m-1. And one Mises-Fisher distribution is given as follows, which consists of the two parameters that you're mapping, which is mu and kappa, which one acts as a mean, which is a mu, and kappa acts as a concentration parameter, in some sense vaguely as a standard deviation, as you would have for Gaussian distribution. And this complicated looking term is just a modified Bessel function. But the good thing about this paper is that they gave us an exact way to compute KL divergence between VMS distribution and uniform distribution. So now, instead of approximating this, we actually have a closed form for this. So this is where we were like, okay, what can we do beyond this? Is there a way where we can actually use this compact nature of this latent space and use hyperspherical VAEs as a starting point to make our VAEs equivariant to different transformations? So the idea is simple here. So we combine these two. And how do we do that? For that, I'll have to talk a bit about what are Kendall-shape spaces. So Kendall-shape space can be defined as a quotient of a space of landmarks, configurations, by a group of translations, scale, and rotations. Here, for this particular definition, here we just take landmarks as a sequence of points. That's it, no other constraints. Just to formalize it a little, we also define, or not we, but people who studied this before us. Pre-shaped space was defined as the following, which is just, for example, if it is, it's just a set of k points in Rm, which is represented as a space of m cross k matrices. So if we can, for example, we already know that we can map these, or we have a hyperspherical VAE that can map our latents to a sphere. So if we can use these Kendall shapes, which are already invariant to these transformations, along with mapping this, then we already have a compact representation, plus we have invariance to these transformations. So if we can make pre-shaped space invariant to transformation and use that as a latent space, our job is done, right? Almost so, right? So the reason this makes sense is that we can map each of these equivalence classes that are found by transformations using Kendall-shaped spaces, and then put these as points as landmarks. So for example, each of these, or each set of these landmarks would then just be representing these equivalence classes. Okay, so how does the Kendall-shaped VAE look like? So this is sort of the pipeline. So we start with different images. For example, here we have an m-ness digit with different rotations. Then we have an equivariant encoder. I'll talk briefly why we need an equivariant encoder there, such that it can, we can extract the parameters we need for our VMF distribution, which is mu kappa, as well as a pose. And then map this to, so if we normalize it, we can just map it to a hypersphere, because we already are we are using VMF distribution, so that's simple. And then, so as we know that when we are at this, here, right? Yeah, when we are in this zone, we don't have any orientation information, right? Because we made this, for example, if this were rotation equivariant, we do not have any rotation information. So how do we then decode it, right? Or how do we get our image back, or with the rotation? So what we do is that the pose that we extracted here, we try to plug it back in here, and then we decode alongside this set of landmarks, so which are invariant to transformations. For example, if we are dealing with rotation, this will not contain any rotation information in spite of this 2 being, say, rotated. This isn't, because irrespective of whatever the rotation will be, this representation will remain the same, because we want this to be invariant. All right, but we still do care about the rotation information. So we are like, okay, we take this pose information, plug it back in, and then decode these 2 things, like this as the input for the decoder. And because we have this, or ideally we have a set of these arrows based on the rotation of these, then we get back our images. So this is sort of the pipeline. Now, again, so why do we need equivariant encoders or decoders? Because if we want these set of landmarks, which we are going to call the shape representation or just shapes, to be invariant to transformations, then we need to make sure that this is also doing that, right? We cannot have any information, but we also do need to extract the pose such that we can get back our images, just because we would like to reconstruct as well, right? Yeah, okay. So this is the Kendall-shape VAE formulation. Yeah, so what we are doing, so the shape, so actually we only get, sorry, okay, yeah. So we only get the points here. The line is just we just match the lines, for example, with the first to the second to the third points, because landmarks are a sequence of points. So whatever the shape that is formed remains invariant to these transformations. And we consider these as an equivalence class. So for all these rotations, we will have one of this. Where each of this image, is related by this rotation. Okay. Right. Okay, so just to dive a little bit deeper, so I hope my animation still works. Okay, so given this image of this cat, we have this shape. So here by shape, we just mean set of landmarks. So there will be these points here. Then we have this pose, for example, here could just be a rotation, could be translation or scale, but we take, for example, rotation, and this uncertainty parameter, kappa, because at some point we would also like to use this model as a generative model, so we do care about this parameter, and hence we model it as a VAE. And once we have these things, we put this into this shape to sphere module such that it can compute, and then we compute the mu on this hypersphere of this dimension. And from that we get our decoder, then we decode our shape along with the pose and get our image back. So for example, if this were a rotated image, nothing changes with our shape. So shape remains the same. The only thing that changes is the pose. And then we can decode it back and we get the same image. Right, yeah, okay. So how do we do that? Just to reiterate, in order to make sure that we have these invariances in place, we take these landmarks x in RMK space. Then we subtract the mean so that we can get translation invariance. So here, so we have subtracted the mean. And then we align it with a reference pose that gives us a rotational invariance. And then we normalize it, and that gives us scale invariance. That way. But of course, scale invariance is a bit trickier than just this, because we are anyway normalizing all of our points to a sphere. So that's maybe, we can discuss this after I'm done with it all. But I think you can see that just by the definition of these Kendall-shaped spaces, all these things can be sorted. Of course, how we code it up or how do we represent the scale part is still something we have not done yet. Okay. All right, so again, just a recipe. We take this as an encoder. Then we have these three parameters that we can extract. Then we have a sort of a representative latent. Then we sample using our parameters that we extracted an encoder, and then we decode it back. All right. But okay, enough about just the Kendall-shaped spaces. Can we improve on the representation capacity of these landmarks? And how so? That's where this work comes in. This is the continuous Kendall-shape VAE part. So the idea is that because here landmarks are discrete and only focus on discrete points, and can we look at it beyond that, right? So can we think of it something more? So this is sort of a viewpoint that we have taken here. So we think of these feature fields as a bundle of fibers that can transform by actions on SOM for just rotations, for example. And these signals can then be mapped to a set of Fourier-like coefficients relative to the basis of irreducible representation of SOM, because we can do that for any of these Fourier-like coefficients, all right? So there's no rule against that. And then we design equivariant encoders and decoders as similar to what I spoke in the Kendall-shape VAE part, such that these fibers can directly be used as landmark itself. So instead of having this discrete approach, we look at it's like sort of mapping a spherical signal in itself as a landmark. And then we have to slightly play around a bit with how to then define a landmark point, or how do we then compute the landmarks, right? So which representation of the signals do we actually compute? So this is where this definition or this figure, I hope, can help. So let me just reiterate this definition, which we present. So we define the pre-shape as following, such that it can be equipped with this pose. I mean, for here we have, for this work, we mainly take SOM, such that we have a rotation part of the pose that describes the canonical shape, and x0 for the pre-shape. And any of this pre-shape lies in an SOM of a canonical shape orbit. So for example, if I had this figure of this bird here, the discrete Kendall shape points would just be these blue dots. And if I were to represent it as just one signal, I would get something. So this is a spherical glyph representation, something like this. But for example, if I had 3 landmark points, again, these are not points anymore, these are representations of signals, such that they could have this continuous element to it, you can see that this versus this could give us more expressivity, right? So there's already some inherent shape information just by these 3 points and the positions it could take with these signals, versus this, which has, I guess, about 8 points, right? Okay. So what do? We are, in the Kendall shape, we have an encoder that predicts k landmarks in Rn, which are normalized to a unit length, and such that the pre-shape is a sphere of dimension 2k minus 1. While in the continuous KS-VAE, we have an encoder that predicts k signals over SO2n, which are band limited to the maximum frequency here, which is n. And then we subtract the mean. So we encode an 8-dimensional landmark, which are then normalized to points that lie on a sphere of dimension 8k minus 1. So just to note, for comparison, we will try to stick to, for example, here, because we have an 8-dimensional landmark, we then compute 4 landmarks for KS-VAE of 2 dimensions, such that we have a fair comparison, but more about that in the experiments. Sorry. Okay, I'll go quickly. Okay, so this was the experiments we did with the KS-VAE. So as you can see that, again, so we have connected these points with line segments as the sequence of the Kendall points, landmarks. So we can see that there is some uniformity in shape that is extracted here. For example, all the zeros have some kind of like an inverted 4-like shape, or the ones are sort of like a 1. Similarly, 3 gives a kind of a Z shape, or almost a Z shape. Okay. So maybe I can leave the details of the experiments a bit later, but I can present the final results. So what we did for comparing our method is that we took the vanilla VAE, then the spherical or hyperspherical VAE. Both of these are non-equivariant models, so the convolutions were, so the convolutions used for this were different than the KS-VAE. And to keep the dimensionality the same, we kept Kendall-shape VAE represented by 4 landmarks, and continuous Kendall-shape VAE represented by just 1 landmark of 8 dimensions. And these 2 models are equivariant rotations. And we compute this, we kind of compare these as we see as just the loss. And the way we look at it is that the faster it trains, the more expressive our model is with same or less number of parameters. All right, so in conclusion, we have a fully equivariant VAE. We have points in latent space that corresponds to landmarks, and that defines the shape. We show that this shape can be truly invariant to rotation and translation. And then the continuous part extends to more expressive landmarks, wherein spherical signals are expressed as landmarks. And this formalism, or this general formalism of Kendall-shaped spaces, takes us from discrete representations to a signal viewpoint. That's it.